Okay, so let's do 15.6, tangent planes, normal lines, and differentials. And this is really fun, and it's pretty easy peasy. So hopefully you can get behind it. So, so far, we've represented surfaces in space using equations of this format. Little z is equal to f of xy. Okay? And when you do have an equation in that format, just as an example, z is equal to, I'll do something easy, x squared plus y squared. That's an equation for a paraboloid, which is, if you look at the graph, it looks like that. Kind of cool. But when you do have a function written like that, it's called explicit form. And you want to know this vocabulary phrase because we're going to go back and forth between explicit form and implicit form. Now, the analog in Calculus 1 and Calculus 2 is when you're given an equation in explicit form that looks like this, y equals f of x. That's the equation for a function given in explicit form. So our explicit form for a function of two variables here is z equals f of xy. Now, what about the more general representation that we're going to need to use in this section? And if you don't rewrite your functions from explicit form into this more general representation, you will get a problem completely wrong. And I like to trick students. It's not that I like to find out if they're listening. And I'll probably give you a problem where I give it to you in explicit form just to mess with you to see if you've listened to this key step one. Get it in a general form. What you want to do is you want to move everything on one side and zero on the other so that you get the general representation that looks like this. This is key. Okay? So if you're given explicit form like this, what do? Well, what I do is I subtract little z from both sides, although it doesn't matter which side you move everything to, just so long as you get zero on one side and all the rest of the junk on the other. And then this stuff, which now has x's, y's, and a z in it, this is what you call fxyz. Okay? So this right here goes in the blank. Right here, little fxy minus z. And I'll just put as an aside, for those of you who like to always do things backwards, what if I wanted to do it in reverse? What if I wanted to subtract the other junk or whatever and move it to the other side? That's fine also. I don't care. Okay, now from what I went over and lectured in section 15.1, and I know some of you still are working on catching up on the homework for that, is you remember when you were supposed to find level curves, step one is set the function equal to a constant? Well, when you're given a function of three variables and somebody says, hey, find the level surfaces, you're supposed to set that function of three variables equal to a constant. This is a reminder. So what does this have to do with anything? Well, right now, this equation has a flavor of a function of three variables, big f, x, y, z, equal to a constant where the constant happens to be a number. Somebody said, hey, we'll make the constant 0. So that is considered a level, one of the infinity level surfaces for the big F function. So that's kind of key, because so now you know it is a surface. You can graph it in 3D if you have a grapher. So just as a quick example, this is just review here. This is a review from 15.1. Describe the level surface fxyz equals 0 for this function. Big fxyz equals x squared plus y squared plus z squared minus 4. Well, if you set this function equal to the constant 0, and let's rearrange the equation a little bit. I think you'll be able to recognize it fairly quickly because we covered those kinds of equations back like in the first week of this semester. Does anybody recognize this?
Is it a sphere?
Yes! Good job, Elo. It is a sphere. Yeah. So this surface, this level surface, happens to be a sphere centered at the origin of radius 2. Fine. Okay. Now let's do another definition. We're going to do a definition of a tangent line. And where are we working ourselves up to? What I want to do before I continue with the lecture is I want to kind of go over some motivation for what we're about to cover. The motivation is, it's an analog for a topic you did in Calc 1. So real quick, in Calc 1, what did you do like a million times? Let's go over it. You did this a million times in Calc 1, trust me. They'd give you y equals a function of x, you know, whatever, some curve. And then they pick a point somewhere and they go, hey, I'm going to pick a point right there. You know, let's say x is equal to c. Okay. And then they go, oh, I'm going to draw a tangent line to that point. So I'm going to try to draw a tangent line. Yeah, it's not a very good line, but I think you get the idea. There's a tangent line. Hey, can you come up with an equation for that tangent line? Do you remember this Calc 1 type of problem?
Yes.
I hope you can. Well, I'm not going to do the whole problem. But how would you get the slope of that tangent line? Anybody have an idea?
Take the derivative at that point.
Yeah. So the slope of the tangent line would be the derivative of the function and evaluated at that point when x is equal to c. And then you would go ahead and use the, you guys remember this equation from like a beginning algebra class? The point slope form?
Yes.
Does that look familiar? So
Yes.
here your m,
Yes.
yeah, sure, of course. Your m would be the f prime of c, and then this point would have like an ordered pair c, and then the function evaluated at f of c. And so in this equation, your y coordinate would be f of c. You'd have your slope. There we go, and then you could rearrange this. So there's your tangent line equation. Boom, done. Okay. So what I want you to get is where we're headed is we're going to try to get, instead of the equation of a tangent line, although I'm going to define a tangent line to a surface here in a moment, we really want the equation of the tangent plane to the surface. So where we're headed, just so I want you to keep your eye on the ball here, is let's say you had some surface, you know, and I'll just make something up. Yeah, you could have like a paraboloid, say z equals x squared plus y squared. That's kind of a cool surface. Woo! Looks like that. And let's say somebody picked a point on this beautiful paraboloid. Yeah, like right there, there's a point, you know, or anywhere really. And then instead of coming up with a tangent line equation, you're going to kind of come up with a tangent plane. So I'll try to draw a plane that's sort of tangent, that just kisses the surface right at that point, and it's a tangent plane to that surface. So I have a better sketch of it here. Can you guys, I know sometimes people don't see this too well. I've had trouble. Can you guys see that okay or not?
Yes.
Yeah.
Yeah, I can see
Okay.
that.
You can see that? So this is kind of like the blue is the paraboloid, and the yellow is a plane that's tangent to the paraboloid at a particular point. So I hope you can kind of see that. So if I kind of zoom in a little bit here, maybe you can see a little bit better. So there's a zoomed in. So when you zoom in, the idea that I hope you got from a Calc 1 class, hold on a minute, let's go back here. Do you remember one of the things from Calc 1 is if you zoom in really close and look at the line compared to the actual curve, and you really zoom in closely, do you remember when you discussed differentials that the tangent line, if you really zoom in, is a good approximation of the curve? Because they're almost the same if you zoom in quite a bit. Does anybody remember that?
It's foggy.
Yes.
Very foggy.
The same type of thing is how we're going to treat it, because we're going to do differentials now in Calc 3. And so if you zoom in quite a bit here, you know, and I mean a bit, so let's see if I can zoom in even more. Let's try another zoom in. So that's another zooming in. If you zoom in like even more, it almost seems like the tangent plane is approximating the surface pretty well, as long as you stay really close to the tangent point. The surface can be, you know, the tangent plane is a pretty good approximation of that surface. Just like in Calculus 1, that tangent line, as long as you stay close to the point and in a nice neighborhood of it, it's a pretty good approximation of the actual curve. That's where we're headed. So that should be your motivation. Okay, so back to the problem at hand. So some definitions here. Let's first define what it would mean to be a tangent line at a surface. So the idea is you have some fixed point that's on your surface S, and you don't want your gradient of big F to be the zero vector, because that would be terrible. A tangent line to the surface at the point P naught is a tangent line to any curve, which, as long as the curve lies on the surface and contains that point. So if I were to draw this idea here, so let's have a surface here. It'll be like a little capping surface. So this will be some function z equals f of x, y, which when you rewrite it in more of a general format, so you can think of it as this stuff right here is your big f, x, y, z here. So you have that. And then I'll pick a point. Let's say that there's our point right there. We'll call that guy. There's your point P naught. Okay, he's on the surface. Now, I'll draw a curve on the surface. As long as the curve passes through this point, there's a curve right there. Fine. So this curve, I'll call it C. It lives on the surface and it passes through that point. Now, let me draw a tangent line to that point, you know, that's tangent to the curve. There's a tangent line. And I can draw any curve. Like if I do, well, I'm going to draw a different curve now. I don't like the one that I just did. I want a different one. Okay. As long as it passes through that fixed point, we're good. And then the new tangent line would look like, it'd still be tangent to the point and tangent to the surface. So that would be the tangent line for that new curve. Okay, fine. So keep going. You guys know vector valued functions because you had a midterm on it like a couple weeks ago. Vector valued functions describe curves, and we can describe either of those two curves using a vector valued function. Say r of t is equal to, you know, some x of t, some y of t, some z of t, where that curve lies on the surface. Fine. Since the curve is supposed to lie on the surface, what has to be true is if we plug in the x of t, the y of t, and the z of t in place of the x, y, and z for the surface equation, it still should make or satisfy the surface equation. So what has to be true? F evaluated at the x of t, the y of t, and the z of t has to still be equal to 0 because the curve is on the surface. So it has to satisfy the surface's equation. Fine. Then what? Now here's the fun part. This is exciting. For me anyway, because especially what you guys covered last week. Let's see if it sticks. If your big F is differentiable, and let's say your vector valued function also is differentiable, and those derivatives all exist for x prime, y prime, and z prime, by the chain rule, which we did last week, you have big F, which is a function of x, y, and z, which is all those x, y, and z's are a function of time t since they are adhering to the vector valued function. If you were to find f prime of t, which we can use differential notation instead, same thing, you'll remember that's going to be the partial of the f with respect to x, that's going down this branch right here, times dx dt, plus the first partial, so this is the dx dt branch, plus the first partial of f with respect to y, times, go down this branch, dy dt. And these d's that I'm doing for the independent variable, it's a single one, those d's have a straight stem, plus, and then last but not least, df dz times dz dt. So that is that. But then because the function is equal to 0 right here above, when you take the derivative of both sides, we're basically taking d dt of both sides of the equation. The right-hand side, so the equals here, what is the derivative of the right-hand side? Well, it's the derivative of 0. 0. So that has to be true. Now here is the really, really exciting part. Doesn't this look like a dot product? you've got something times something plus something times something else
The old dot product.
plus something times something. Yeah, that left-hand side looks like a dot product between what vectors? The gradient for big F, del F, and the tangent vector, r prime of t. So this implies that the gradient of big F, which basically looks like fx, fy, fz, which if you use other notation, so this is del F right here, you could, it's df dx, df dy, df dz, and then the tangent vector to the curve, which is r prime. And what's true, and this is what's really cool, is that the gradient for the big F function is tangent always to any velocity vector, any curve that you do on there. So all the tangent lines lie in a plane that is normal, and when we're using normal in this conversation, it means orthogonal to the gradient at the point P naught. Now, you probably don't get this whole idea of this right here. You're probably like, huh? I don't get it. I'll just accept it. I want you to see it physically. So if I go over here to my picture I was doing here, I claim that the gradient right at this point is sticking out of the surface, del F. And if I start graphing all of those tangent lines, so if I start like picking different curves, like, hey, I'll pick a different curve through this point, and I'll do a different tangent line. And so I'll have all this collection of these tangent lines like a bed. And so I claim that all those tangent lines to all the different curves all make 90-degree angles with this gradient, because the gradient is orthogonal to every single one of those tangent lines. And so all of these tangent lines together, if I keep drawing them like this, they, through that point, create sort of a bed. And the bed, the mattress for the bed, if you will, is that tangent plane. So all of those r prime vectors live in this tangent plane. And this tangent plane is orthogonal to the del F. It's like sticking out of the plane, which is going to be helpful because when we have to come up with an equation for this tangent plane, you remember from when we discussed tangent planes and you know, getting equations for planes rather. You need two pieces of information to get an equation for a plane. A point that lives on the plane, and we have one. It's this fixed point right here, P naught. And you need a normal vector to the plane. Aha, that's just going to be the gradient, del big F. So we have it. So that's the cool thing. So now we're ready to do the full-on definition. If you have big F and it's differentiable at some fixed point, P naught with coordinates x naught, y naught, z naught, on your surface S, and the surface has to be given by this general representation. If you do not have this general representation for your surface, where it looks like the level surface where the constant is 0, this isn't going to work. And your big del F isn't the 0 vector, then the plane, which is the tangent plane, through the point P naught that's normal to that gradient is called the tangent plane to S, S is your surface, at P naught, at the point P naught. Now we can also discuss a line that's normal to the surface and the line that's piercing through the surface that has the gradient del F as your direction vector. That is called the normal line to S at the point P naught. Cool. Okay, so if I were to draw the normal line on that crazy diagram that I just did, I know it's nuts. It's getting kind of messy, but I'm going to scroll back up. Boy, this diagram's getting pretty verschnagled here. Woo! So if somebody said, hey, where's the normal line you're talking about? The normal line is this line that pierces through the surface. This purple line I have here, this is the normal line that has the gradient as its direction vector. So that's cool. That's a picture of it. Okay, now that we have the definition for the tangent plane and the definition for the normal line, we can now discuss getting the equations for those guys. Okay, but we do want to have a GPA, a general person's agreement, that when we're being asked to find either the tangent plane equation or the parametric equations for the normal line, that gradient isn't the zero vector, because otherwise we're screwed, because we're going to need that guy. When would that happen? Well, if you have a sharp corner or something weird happening at your point where you're trying to get a tangent plane, you could have this gradient be the zero vector, so it'd be a nightmare. Okay, so recall that the equation for a plane, if it contains a point P and has a normal vector n with components A, B, and C, this is just a little review here in case you forgot, because I know you probably have other classes and you might forget all your important things in this class. I'm just doing this as a favor to you. Does everybody remember that this is the standard form for the equation of a plane?
Yes, ma'am.
Yes.
Like, okay, you know, like a month ago. Okay, just checking. Okay, so we're going to use that formula to get the equation of our tangent plane, and you should already kind of see it happening, I hope, that the A, B, and C are simply going to be the components that you're going to take from your gradient, because from my diagram up here, if you'll notice, this gradient is the normal vector to your tangent plane. So now you do have to evaluate that. You want pure numbers to be your to be your ABC. I don't want to see X's, Y's, and Z's in there. So your fx evaluated at the fixed point, that's just going to be some pure number, that's a z naught, times x minus x naught, because you're using this fixed point as your, plus you'll plug in the point x naught, y naught, z naught to your partial with respect to y, and that'll be the second component for your normal vector, and then finally fz evaluated at your point, and then z minus z naught. So this is the standard form. Now Briggs gives something a little different, of course, because me and Briggs disagree a lot of times on these kinds of things. But I claim my equation is superior because it works for whether or not your surface is given to you in explicit form or implicit form. So I really encourage you to use your lecture notes, and don't always believe every time you click the view an example button, because it's not that good sometimes, can be confusing. Now what about that normal line that's piercing through your surface? How do you get the parametric equations for that normal line? Very easy. You got your direction vector, that's the gradient. You have your point on the line, that's the fixed point. So your parametric equations for your normal line can be found very easily. It'll be the point x naught plus the first partial of big F evaluated at your point, you want a pure number there, times your parameter t, and then the other ones look very similar except for the y. You're going to evaluate the first partial with respect to y at the point times t, and then your last partial. Okay, and so these are really easy and formulaic problems. Like these are going to be like free points on your quiz next Sunday. I want to mention that your quiz this coming Sunday is shorter than the quiz you just took. I know that for those of you who took your quiz, you're probably like, oh my God, 16 problems, this is nuts. Well, you know, you were covering 3 sections there. I put like 5 problems that had to do with partial derivatives and second partials, and then I put like, I don't know, 8 problems that had to do with chain rule, because chain rule is important. And some of those were easy. It was just like, hey, pick a tree, baby. So they were multiple choice. And then the last 3 had to do with directional derivatives and gradients from the section 15.5. So it wasn't too crazy, but this coming week, I'm just going to put 8 problems on there. Like, you know, half of them will be roughly from this section here, and the other half, and I'm being, you know, it could be a little more, a little less, from 15.7. So that's good news. Okay, so now let's do an example or two. I got plenty of examples of using these formulas that we just got. And again, you're going to see this is very formulaic. Just make sure you follow the step-by-step procedure that I've outlined here, and then you'll be safe. So let's say you're given a surface that's represented implicitly. So this is an implicit function of x and y. Well, why isn't it explicit? So just a little reminder, recall at the beginning of the lecture today that explicit form is this. This is explicit form, and this is obviously not explicit form. Now, sometimes if you're really good algebraically, you could take an implicit function of x and y and rearrange it so that you could solve it for z and get it into explicit form. But this one would be really hard to do that. And some of them are just downright impossible. So if you'll recall from Calculus 1, you actually studied this idea of explicit and implicit. So let me just remind you that when you were in Calc 1, and you were given something explicitly like y is equal to f of x. Okay, fine. But remember, they did implicit also. So the implicit type of equation of x that you might have been given in Calc 1 could have looked like this. Sine of x plus y, minus x squared y equals, y cubed plus 15 or something like that. Good luck trying to isolate y and get that equation, which is implicit, in explicit form. It'd be impossible. But you can still talk about it and any type of equations that are, excuse me, in explicit form, because they still represent some sort of curve. It may not pass the vertical line test or anything, but you can still talk about, finding slopes or, in our case, finding tangent planes, and that's still doable. So that's what we're doing right now. And for those of you who are like, well, really, I don't buy it. I could easily go into I'm just wondering what that surface looks like. Let's just check it out. Sometimes the GeoGebra, for those of you who really like to go into and graph stuff on your own, if you're motivated, I encourage it. But I sometimes don't have very good luck with GeoGebra, especially when I'm doing these implicit functions of x and y, and maybe it's just me. Maybe I'm not an expert with GeoGebra and I just need to take a class or something on how to do it. Probably is the case, but they always give me an error anytime I try to type in something like this that's implicit. So this is an implicit function of x and y. Oops, I screwed up. Y squared, uh-oh, I really screwed up, squared, and then y squared z. So what I like about my new calc is that it always gives me, ooh, that's kind of an interesting looking surface. Wow, that's cool. Nice. So, if you find the point 1, the point we're trying to deal with is the point -1, 1, -1, which is somewhere on this surface. We could locate it, and we're just being asked to, come up with a normal vector to the surface as well as a tangent plane to this surface. So that's kind of cool. I always like to change colors. Ooh, pretty. What else? Oh, that's too dark. Can't see it. Okay, so this is a really cool surface, and we're being asked to find a normal line and a tangent plane. Fine. Okay, so back to the hand-to-hand combat here. So you need to do step 1. If I do not see you do step 1 on your handwritten work and you magically get the right answer, I'm going to just give you 0 points. So I'm just telling you right now what the deal is. So don't tell me, well, I do stuff in my head. Nice. Put it on paper. Step 1, get everything on one side and 0 on the other. Does it matter which side I'm getting everything on? No, because when we're, at least in this section, I want to warn you later on when we are doing some other things or when we deal with oriented surfaces, it will matter which side you move all the junk to and which side has the 0, because you want something to either have a vector punching out of the surface rather than pointing inward. But here I don't care, because if I have a surface, let's say I get everything on one side and 0 on the left, say, my normal vector might be punching out, my del big F, And because you got all the rest of the crap on the right-hand side and you're 0 on the left, no worries, your del F is still going to work for us. Your del F will be pointed the opposite direction. But either way, both of us will be correct because our big del F, that big old gradient, is still going to be normal to the tangent plane. You know, so it doesn't matter if it's facing out or in. So we don't care, just so long as you get everything on one side and the 0 on the other. Okay? So this is your step 1. You need to get this general, I'll call it gen rep, where everything is on one side and 0 on the other. So I'm just going to move everything, what the heck, to the left. So I'll keep the x squared y cubed plus 2xz cubed. I'll subtract 4 from both sides, and I'll subtract the y squared z from both sides, and then I'll have equals to 0. So this stuff over here on the left, that is a brand new function that you are going to name big F. And he's a function of 3 variables, and he's the guy you're going to get the gradient for. So, and which happens to be a normal vector. So when they say find the normal vector to the surface, this is the same as the gradient del big F. It's the same. And you'll have answered part A perfectly. So let's go get del F, which is simply a vector that has the first partials in it, and then we'll evaluate that gradient at the point in question. So let's do this. Here we go. This is an easy function to differentiate because it's just a big old polynomial. So what is the partial with respect to x of this big old polynomial? We'll start with the first term. Anybody want to help me out here? Otherwise, I'll call on people because I know there's people in the room.
The first term would be 2y cubed x.
2y cubed x. I'll go for that. If you don't mind, I'm going to rewrite it in more conventional terms format where the x and y are, alphabetical order. Okay. Anything else, or are we done?
No, we still got the last term.
Okay, I'm gonna hold on a minute, Nick. I get that you're awake. I'm gonna call on someone else. What the heck? How about Christopher Guadarrama? Are you in the room? Morning.
Hello, you said
What do you think would be our next term, if there is any, of finding the partial of big F with respect to x?
So 2xy cubed plus 2z cubed.
Perfect. Thanks, Chris. That's awesome. Okay, let's see if anybody else is there to help me. How about Anthony Ocampo? Anthony, are you awake? You want to help me start FY up?
Yeah.
Okay, what do you think should be the first term for that partial of big F with respect to y?
3x squared y squared.
Yep, good job. Thanks, Anthony. Okay, how about Emily? Are you there?
Yeah, I'm here.
Awesome. Is there anything else that I need for FY, or is FY done and complete?
It should be minus 2yz.
That is correct. Thank you. All right. God, everybody is on a roll today. This is awesome. This is what I like to see. Okay, let's see if there's anybody else around here. How about Isaiah? Isaiah, are you there?
Yeah.
You want to start us off for the partial with respect to z?
6x z squared.
Yep, correct. Okay, how about Danielle? Danielle, are you there? Danielle, I'll check the chat in case you don't have a microphone. That's understandable. No? Danielle not there? Okay, David. David, you're in the room, right?
I assume so.
You're semi-awake, right? What do you what do you think is still left for the partial with respect to z, or am I done?
Minus y squared.
Yep. Okay, congratulations. I think we're done. And that is the gradient, but they want the normal vector to the surface at this point. So I'll have to, I ran out of room. What else is new? If I evaluate my gradient at this point, so now I have to do a whole bunch of substitutions, and I'm going to kind of do this quickly. This term is going to end up being a -2, and then this one, -1 cubed, I'm going to have a -2. And then the second component, I'm going to substitute -1 and that's going to be 1, and that looks like it's going to be 3 plus, this is going to be a minus, so it's going to be 3 plus 2, and then this one's going to be a -6 minus a 1, and I think I'm going to get -4, 5, -7. Okay, and this is the answer for part A. That is a vector that is normal to the surface. So it's basically it's the gradient, and it's punching out of the surface. Okay, great. And we're going to use that gradient for the rest of the problem. Basically, part A helps us do like the rest, which is nice, because in part B, where they say, okay, find an equation in general form for your tangent plane to the surface at the point, you have a point, you have a vector, this is normal, this is a vector normal to the tangent plane. So you have the two ingredients that you need to come up with the standard form. So I'm just going to hit it. So I'm going to have a -4 times parentheses x minus a -1 plus 5 y minus 1 quantity minus 7 times z minus a -1, and that whole mess is equal to 0. And then to get general format, you know, you're going to distribute. So I have -4x minus 4 plus 5y minus 5 minus 7z minus 7. And then rewrite this where it looks a little nicer. So I'll keep the x, y, and z terms on the left. Oh, that's a terrible looking 7. I apologize. That 7 looks like a z. And then I'll move all the constant terms to the right, and I think I get 16. So there's general format for the equation of the tangent plane. Beautiful. Okay. Now they want the parametric equations for the normal line. Well, we have a direction vector for the line. It's the gradient. We got a point. So the parametric equations are easy to get. You got your point here, so I'll just go -1, 1, -1, and then you just use these gradient components for your direction vector components. So -4t plus 5t minus 7t, and there's my answer for part C. Okay, letters D and E. What do you think would be the answer to letter D? They want us to find del F to the surface given by fxyz. We already did this in part A. And this is the more general del F, you know, at any point. So at any point, you're just going to have the del F, which I don't feel like drawing up again, but it would be this gradient right here. That gives you the del F to our level surface. So you're done. Letter E, what about level surfaces? So now consider any level surface, fxyz equals c. That's some level surface. What is c for the point 321? Well, you already know what your surface looks like. So you're just going to substitute 321 into this function up here, right here. So in place of x's, you'll put a 3. In place of y's, you'll put a 2. In place of z's, you'll put a 1. So it's just substituting. And you'll set it equal to c, and then you'll just get c right off the bat. Go use a calculator. And I get 9 times 8 plus 6 times 1 minus 4 minus 4 equals c. And I think c is 72. Not too hard. Okay, we're done with that entire problem. See how formulaic it was? Questions?
I'm good.
So if I put this problem on a quiz on this coming weekend, would you be okay with it?
I think so.
Yes.
Maybe on the second try.
On the second try? Well, another person who's teaching a Calc 3 does not give 2 chances on their weekly quizzes. And I wasn't going to either. And then I got some inspiration. One of my former students, who's an electrical engineering major currently at State, and she helps me grade, she goes, I think you should give them 2 chances for good practice. And I went, Okay, so you can make a check out to Natalia. No, I was going to joke around that you should pay her off. Okay, here's a different type of flavor of a question. Remember I told you I might try to trick you to see if you know the difference between explicit form and the more general representation? This is it right here. So be aware that on the quiz this coming weekend, quiz 6, one of the problems will be easy peasy. It'll be like this problem we just did where you're given some weird implicit function of x and y like that. And all you have to do is move everything to one side, 0 on the other, and you're fine, just like we did. But what if I give you the surface equation written explicitly? And this is where I catch people to see if they really know their deal. So I'm going to show you. It's really easy if you just pay attention and watch what I'm doing. It's pretty much the same procedure, but the little twist is if you know what it means to be explicit. So check out this equation right here. This represents a surface, fxy is equal to 16 minus 2x squared minus y squared. And I'm gonna do all kinds of stuff with this. This is gonna be gonna have a little bit more to do than the last page. I'm gonna actually bring in some of last week's material into the conversation, like directional derivatives and stuff. And I think some of you can use it because what I'm getting when I'm looking at some of the homework scores, especially for directional derivatives, that was Friday's lecture, I'm a little kind of worried. So I encourage you to go do that homework because it's not that hard. Directional derivatives are very formulaic. You got the point where they want the directional derivative. They give you the surface. They give you some direction. All you need to do is make sure your direction vector is unitized. You take the dot product between your gradient and your unitized direction vector, and boom, you have the directional derivative. But the reason why I want you to see all this in this one problem is this is going to help you understand the difference between the two-dimensional gradient and the three-dimensional gradient. And if you don't get this page, you are doomed. So I created this example. You will not see this example in the book. I did this because I want people to see the distinctions between some of last week's material with gradients and this week's material with gradients. So if you just stay awake for like the next 10 minutes, you'll be able to get this very easily for yourself. Here we go. First up, they're asking you to find little del f. So see how they have like a little f there? And here's little f. So this is a fancy disguised way of saying go get the two-dimensional gradient, not the three-dimensional that we've been doing since the start of the lecture. So you should know that there's a difference. So little del f is going to be a two-dimensional vector, and it'll simply consist of the partials fx and fy for this explicit function of x and y. This is an explicit function of x and y. Okay, and I'm going to do this real quick. It's just negative 4x and negative 2y. Boom, I'm done with part A. Done. Move on. Okay, letter B. Use the gradient of f to help you find the directional derivative for the function at the point P, which has coordinates 1, negative 2, in the direction of the point Q with coordinates negative 3, 4. Now, folks, when they're asking you for a directional derivative, which is basically a slope, you are to use the little gradient, the little two-dimensional gradient. You need a two-dimensional vector, like when you're standing on the surface. Let's say you were standing on some mountain here. Here you are with your skis. You know, here's you. Hey, I want to know the slope in that direction. Your direction vector is actually lying in the xy plane, and that's your gradient, or your, excuse me, it could be a gradient if you're pointing in the direction of gradient. So this is the direction you're pointing in, and you want to unitize it, so I'll call it u. So the direction you're pointing in is a two-dimensional, and so you can think of yourself holding a compass flat in your hand, and it's a little arrow pointing you in the direction you want to find your slope. Not a 3D. If you accidentally use the 3D gradient to find this directional derivative, I'll just take away all your points. Okay, now on this coming week's quiz, I'm not going to throw in a review problem of the directional derivative. I'll kind of keep it to the matters at hand. But when the midterm hits, where I throw just a jumble of everything in no particular order, you want to be very clear about what gradient is used in what spot. And if you're not, it'll be a trouble. Okay, so this is basically last week's material that we're doing right here in part B. Okay, so first off, I'm going to form the vector PQ because this is going to give me the direction I want to find the slope, terminal minus initial, terminal minus initial. And PQ has components -4, 6. The next thing I want to do is I need to unitize PQ. That's next up on the agenda. So I'm going to need the magnitude of PQ in order to do that. So the magnitude of this PQ vector, ooh boy, is square root of 52. It turns out 52 is 4 times 13, and you can reduce that radical to 2 square root of 13, which is nice. So then U is going to be the vector -4, 6 divided by this magnitude, and then you'll reduce to lowest term. So I get, oh shoot, that's what I get. I get for leaning my hand on the. So I'm going to get, after reducing, -2 over square root of 13 and 3 over square root of 13. Okay, and now I want to evaluate my little gradient, little del f, at the point 1, -2. And remember, this is little del f up here. And that's going to be -4 times 1 and then -2 times -2. So those components are going to be what? -4, +4. So the directional derivative in the direction of your u for this function, remember, is the dot product of your little two-dimensional gradient and the unit vector that you're trying to find the slope of. So you're going to take your gradient and the dot product with this unitized vector. So you'll get sort of a weird number, which can happen a lot of times when you're finding directional derivatives. So I get, when I'm finding this dot product, ooh, that's weird, 20 over square root of 13. Okay, I'm done with part B. I just found the directional derivative, which is a slope for the surface in the direction of the PQ at the point P. Okay? So is everybody okay with this? You know, if we were to find, you know, just for kicks and giggles, because I always like graphing this stuff if I can, how would I graph this on my my thing here? Can I type in fxy? I'm not sure if it'll let me actually. No, I don't think it will. So just to let you know, it doesn't let me do that. So why not? What do I have to replace the fxy with in order for me to graph using my grapher? Does anybody know what I should replace that? Yes, that's going to be the trick to do the rest of the problem. If you are listening, write that down in like big letters, like I'd use fancy colors or whatever else that you need to. So in using my grapher, when I graph this surface, I'm going to go z equals v16 minus 2x squared minus y squared. And it should be some sort of paraboloid. Let's just check it. Oh, there we go. Let's go. Oh, I need to zoom out a little bit. Well, you can see it if I kind of twirl it around a little bit. There he is. Can I zoom out? Oh, there we go. Let me zoom out again. Let me zoom out one more time. Yeah, there we go. So I hope you can see that this surface is kind of pretty. It kind of looks like it's an upside down paraboloid. I don't like this color. It's not too cool. It's hard to see. There we go. It's actually should be oriented downwards. So if I try to stop the rotating. Okay. So I hope you can appreciate. You can kind of see that if you were finding a slope, you'd probably get a pretty steep slope depending on where you're headed. It is a very nice surface. So now we can go back to the matter at hand. You want us to do some more stuff with this surface. So we already found the little gradient and we found a slope. So what now? Well, we want to find a vector that's normal to the surface. So if our surface is this downward facing paraboloid like this, you know, at the point 1, -2, 10, so, you know, 1, negative 2, 10. I'm going to say it's like maybe somewhere here, roughly. Right there, we want to find a vector that's normal right at that point. Okay, well that's a 3D vector, because if I were to actually graph a vector that's punching out of the surface, you know, it's making a 90-degree angle, it would look something like that. That's a normal vector to the surface. And I claim it's del big F, which is a function of 3 variables. So your job is, step 1, you need to get the general representation first. And if you fail to do this step 1, you'll not be able to do the rest of the problem correctly. You want to get everything on one side and 0 on the other. So after replacing this thing with z, so your function right now looks like z equals 16 minus 2x squared minus y squared. Get everything on one side, 0 on the other. It doesn't matter which side. It's going to be easier for me to get everything on the right side because all I have to do is subtract z from both sides. So I'll go with that. And then this stuff over here is your big F function. So this is a level surface for big F where the constant, instead of just any old constant, it's 0. But it's a surface. And what is a surface? It's a paraboloid still. The paraboloid hasn't changed. It's still a paraboloid. But you're now going to be able to use this representation to go get your 3D gradient. So the answer to letter C is going to be the 3D gradient evaluated at the point 1, negative 2, 10. So the 3D gradient is going to look like negative 4x, negative 2y, and then when I differentiate that whole thing with respect to z, what do I get? I'm going to call on somebody. Okay, Veronica Ramos. I know she's in the room, right, Veronica?
Yes.
You are. What is the derivative of this mess right here? I'm circling it.
-1.
Perfect. Now, because it's a -1, what that means is that it's actually not punching out of the paraboloid, kind of like my picture is doing. It's actually, it's still orthogonal to the surface, but it's punching inward, into the interior of the surface. And that's fine. No big deal. It's still a normal vector, so we're cool. So I'm going to go with it, and then they want me to get it at the point 1, negative 2, 10, so I'm just going to do some substituting here now, and substitute the point 1, come on, there we go, negative 2 and 10, and I get this vector, and this is going to be the answer for letter C, the vector with components -4, 4, -1. And we're done with part C. There's a vector that's normal to the surface. Okay, now we're going to get the level curves for the surface. So how do you get level curves? This is review.
Constant.
Yes, this is a review. So you're just going to set it equal to a constant. Set what equal to a constant? Well, you're just going to go 16 minus 2x squared minus y. You're setting little f equal to a constant, not your big F. That's why this is tricky. So, because you're getting level curves now, not level surfaces. I don't want z even in the equation. So now if you rearrange this, and I made it look somewhat pretty by, I'm just doing some rearranging here. I hope you can appreciate that the level curves would be ellipses. Okay, so if you were like in a helicopter or an airplane looking down on this surface so that it appeared, you would see not circles, but you would see ellipses looking down on the surface. So like if you were to draw a contour map, it would, it would most likely look something like this, where you're looking down on this paraboloid from above. Okay, so that would be graphing your level curves, which I'm not asking you to do, but that's just a general thing. And now letters E and F, write an equation of the tangent plane to the surface at that point, 1, negative 2, 10. Well, you know, if I were to draw a tangent plane, there's the tangent plane. We already have a normal vector. It's this guy, our answer from part C. We already have a point, so we're almost done. You just have to use your knowledge of finding equations for planes, and you already know this because I trained you to find equations of planes, and you did that in your midterm 1. And so there's standard form, but if they want general form, that means multiply all this mess out by distributing and so on. And so after multiplying this out, I get negative 4x plus 4 plus 4y plus 8 minus z plus 10 equals 0. And then when I rearrange it so it looks nice and pretty, where I like all the variables on one side and a constant on the other. I know sometimes my math lab likes you to write these where they solve it for z, which is fine. Which is fine. That's how they roll. Okay, so there's the equation. Oops, I think I screwed this up. Oh, you know what I wanted to mention? That actually should be negative 22. A lot of times, and this isn't so much on my math lab because my math lab is pretty forgiving. They probably accept this answer. But, you know, there's a lot of negatives going on. This is a very negative equation. Well, what do you mean? Like that's a negative, there's a negative, and there's a negative. Very negative. So a common thing, if there's so many negatives in one of these plane equations, is multiply both sides of the equation by -1, just so, and it's equivalent, just so it's not so negative. So the answer I have in my notes looks like that. Okay? They're both correct, though. I mean, I'm okay with either one. I'm not going to go crazy on you, all right? So did the quiz give a really infuriating variable and number combinations like 2 and z and 5 and s? I have no idea which problem you're talking about, David, but see me after class and we'll take a look at it, okay? I'll try to figure out what you're talking about. So we're going to write the parametric equations now for the normal line to the surface. So the picture of that would be, I've got my paraboloid. We already have a picture of the tangent plane. What would the normal line look like? Well, the normal line is just piercing through that paraboloid at that point, making a 90-degree angle, and we already have the gradient. He's our direction vector. So you don't really have much to do here when they're asking you to find the equation, the parametric equations for your normal line. You got your point, so I just put those coordinates down, and then use your gradient, your 3D gradient. That would be this guy up here. It's not working. Like that. And that helps you get your coefficients of your parameter t. So there you're done with letter F. And now letter G, you'll see letter G on your My Math Lab too. So I used to not have this on my lecture notes, and I noticed my Math Lab loves this. So which vector, del F, the vector found in part A, or the normal vector you found in part C, would give you the direction of the maximum rate of increase on the surface at the point 1, -210. Oh no, I misspoke. I actually would put this in my lecture notes. This is the grand finale of this problem. Like, I want you to really focus up here, like focus your eyeballs, because now we're going to answer this question. What is the difference between the little gradient, del of little f, versus del big F? Like, when do you use which one? And we'll answer that question right now. So which of the vectors, of which of those gradients, the two-dimensional one or the normal vector one, that's del big F, the 3D version, would give you the direction of maximum rate of increase on the surface at that point that we've been talking about the whole page? Anybody want to guess?
Oh, big guess.
Yeah.
Okay, you want to do a vote, like polls? Let's see. No, let's do an edit. Does it let me do it? No. Wow, that's really weird. Never mind. Too much trouble. I'm going to have to learn how to do polls better. Do I have any options there? No, I don't. Okay, never mind. Okay, so it turns out, folks, and I know you're probably going to guess wrong, because I heard some folks screaming out, big F, and it's like, no, no, no. It's little del F. That's where you go if you want to increase your, that tells you where to go, like if you were going to increase your slope. What about big F? What about big F? Ah! Big F, if you look back to the picture here, remember that big del F, and I'll draw the other version where it's punching out of the paraboloid instead of punching in, just so it's easier to visualize. Big del F is going to basically get you off of the surface. Like it's going to like eject you into space. You know, you'll blast off. So that's not going to be the one that's going to point you in the direction of increasing your slope. If you were standing here with your skis going, hey, which direction should I ski if I want maximum slope? Or go in the opposite direction so you could go downhill. This big del F is going, hey, get a jetpack, strap it on, and blast off into outer space. No, that's not giving you the direction for maximum slope. So big del F is the one. Well, little del F is going to give you which way to go if you want to increase your slope or decrease it. Well, what about big del F? What is that even good for? Who cares about big del F? We do, because you use this guy to get equations of tangent planes. That's what he's good for. Well, what else is he good for? Well, I can't tell you that because that's why you have to keep taking the class. There's more to it. Okay, so that is the distinction. Okay, any questions on that last page? Comments?
We were finding, I think we were in the last section with gradients. When we were finding the rates of maximum increase, were we dealing with 2D vectors or 2D gradients?
Yes, all of last section, that directional derivative section, which I think is what, 15.5, that had to do with the 2D gradients. Only.
Okay, that makes more sense now.
Like, go back and do all your homework over again with this newfound knowledge that they gave you explicit functions of x and y, and they said, hey, go get the directional derivative for this guy and that guy. The reason why you weren't given the implicit functions to find directional derivatives is, how do you get dz dx and dz dy of an implicit function? You had to use the implicit differentiation formulas. Remember that?
Yes. Mm-hmm.
So like when you got everything on one side and 0 on the other, do you remember that, for example, the slope of the implicit function, you had to use this implicit differentiation formulas?
Right.
Are these looking familiar at all? You probably had a question or two on the quiz that had to do with that. So that's the point. Does that help make a distinction a little bit of what's going on?
Okay, yeah, because that last letter caught me a little bit off guard. The
Yeah.
letter G.
Yeah, I know it does a lot of people because they just don't get it. They go, oh, it's all the same. It's just gradients. No, it ain't. And the book, most every book I've looked at does not do a very good job of making this distinction. Well, Briggs sucks really bad. They try, but they just do a horrible job. Larson tries to do a little bit better. They're not as bad, but I just haven't found a book that does it yet. And that's why I include it here in my lecture notes, because it hopefully gives you a little bit more insight so you can start making connections in your brain of all the stuff that's going on. And I know it's a lot. Like, I see some of you are getting, use a term from England, gobsmacked by where the course is headed right now, because you thought it'd be a little bit easier than it's getting. But it's getting to what it's getting. Calc 3 isn't necessarily a cakewalk. Well, certainly it's not sequences and series, thank God. But still, you got to work it. You got to, every day we meet, you're going to be learning new stuff. I'm not slowing down. I don't have time to go, hey, let's go back to chapter 14 again. No, we're moving. Now, here's something they don't cover very well in Briggs at all, but I do, because I think it's important. Because I want you to recall, do you recall that when we found the equation, or excuse me, the angle between two planes? Does anybody remember this?
Yes.
Yep.
If you don't, let me remind you, because you're going to need that type of knowledge in order to even understand this page. If I ask you for the equation, or the angle between two planes, you first got the normal vectors to these two planes, which you could easily cherry pick off of the equations for the planes, just the coefficients of the x, y, and z. And then you use a formula that you learned in the first week of class that says, hey, the angle between two vectors is the dot product divided by the product of their magnitudes. But then you had to do something a little extra, because you want it to ensure that you got the acute angle between those planes and not this angle on the other side over here, we'll call it alpha, which is obtuse. We wanted the angle that was between 0 and pi halves, so you put absolute value bars just to guarantee that you'll get the acute angle. Okay, now let's go to this topic. When you get one of these cool tangent planes, you know, that we've just been getting for these last couple examples, what kind of angle is it making in reference to the XY plane? You know, how much is it tilted compared to the XY plane? Because that's sort of our benchmark, our touchstone. So since the XY plane, when we use this formula, can anybody think of a quick normal vector to the XY plane? Because he's going to basically be the bottom plane here.
K or Z?
Yeah, whoever said K, you're on. You're awesome. K. K hat is an obvious vector. There's K hat. It's just the unit standard vector there, pointing in a positive Z axis direction. He is the normal vector for the XY plane. So when we were finding the angle between two planes, this bottom plane here, the N2 for us will be K hat. So here is the formula. So I already did this formula up here. So you can, that's that. Okay, we did that. Now the vector K is orthogonal to the XY plane, so we're going to use him for our formula to find the angle of inclination. So here's the angle of inclination. You're still going to have a cos theta. You're still going to take an absolute value of a dot product, but it's going to be your gradient of your big del F. That's the 3D vector that's normal to your plane. And you're going to take the dot product of that with K hat. And then you'll divide by the product of the magnitudes. But one of these magnitudes you don't even really need to go out and get, because you already know what this is. What is the magnitude of K hat?
1.
Yeah. So really, your formula just ends up reducing to the absolute value of your big gradient, your 3D gradient with K hat, and you divide by the magnitude of your big gradient, you know, and you're good to go. Okay. So let's use that knowledge to do example 4. So by the way, do you think that one of these is going to be on the quiz this Sunday? Yes. This is like free points, people. Come on. You should get an A on this problem because there's nothing really to do. So they want us to find the angle of inclination for the tangent plane at this point. For the surface given in example 2 above. So the surface was this guy. So remember, we already got the gradient. We already did. And remember, we got everything on one side and 0 on the other. Just to remind you of how you tackle this. You first do this. You call this stuff on the left your big function of f, x, y, z. And then you go get big del F, which is a nice vector that has the partials, fx, fy, fz. And then you evaluate del F at the point -1, 1, -1. And we did this already. And I think from example 2, we got -4, 5, -7. This is from example 2. I just don't want to do this one all over again because I want to kind of move on. And so then the cosine of this angle of inclination is going to be the absolute value of this gradient, 3D gradient, dot product with the K vector. That just has component 0, 0, 1. And you're going to divide by the magnitude of this gradient, okay, and then you'll get absolute value of -7 divided by the square root of 16 plus 25 plus 49. Oh, good Lord. I think that's 7 over square root of 90. And I'm not even going to simplify the radical because my theta is simply going to be cos inverse of 7 over square root of 90. And I'm going to round to the nearest, what did they say, nearest whole degree. I get 42.45 degrees. So I guess if I round to the nearest whole degree, I'll do approximately 42 degrees. Okay, and that's your angle of inclination. That's how much your tangent plane is tilted, if you will, compared to the ground, which I think is good to know, personally. It's good stuff. So let's revisit this idea once more, comparing your gradient that's a 2D gradient versus your 3D gradient, okay? So some more stuff you should know about the differences, okay? Little del f is orthogonal to the level curves of little f. But big del f, that's this guy here, is normal and orthogonal, essentially, to the level surface through the point P naught, okay? So, and that's an addendum, if you will, to the fact that back in, I think, section 15.1, we may have discussed, or last week rather, we discussed the idea of orthogonality to level curves and surfaces. Okay, so I'm gonna, at the risk of being redundant, little del f is a vector in the plane, whereas big del f is a vector in space. So please know the difference, okay? And once again, I use little del f when somebody wants to know a directional derivative or the direction I need to go to get the steepest ascent or descent. I use big del f when somebody asks me to find the equation of a tangent plane or parametric equations for a normal line. Okay, that I basically just told you all my pearls of wisdom. Okay, so let's do example 5. I'm not done, man. This is like, it just keeps going. I think this is my last problem of the day, though, and then I'll have completed this section. Is that right? No, it isn't. I still have differentials. I may have to wait till next time to discuss that. That's okay. We'll stop after this example, and then we'll do differentials next time, and then we'll start finding extrema next time, which is very exciting. Why is extrema exciting? Well, we're going to finally do what you did in Calc 1, but we'll do it in 3D next time. We're going to find maximums and minimums on a surface, which is way cool. So stick around. And you're going to need second partials to do that. Okay, so last example of the day. Woohoo! And afterwards, I'll stick around if you have any quick questions about either the lecture or if you want to ask me something quick about the quiz. I don't want to get too much into that yet, but okay. You actually did example 5 in a different way. So let me just, before I do example 5, let me remind you of a similar problem because it's going to have the same type of flavor. So if you recall, and I think this was a problem I put on midterm 1, so maybe you'll remember it, or maybe you'll remember it in a bad way, I don't know. But remember, if you had two planes will either be parallel to each other or they'll intersect in a line. And so this line of intersection, oops, I didn't do so well there. Yikes. This line of intersection is kind of cool because on the midterm I said, hey, go get me the parametric equations for that line of intersection. Ooh. So let's walk through the choreography that we used to do this problem that was on the midterm in case you spaced out or you forgot. Because we're going to do the same strategy on this problem. So if you understand the midterm problem, then you'll totally understand how to do this one. So if you recall that this line of intersection, we needed a direction vector. So the direction vector can be found pretty easy by first getting the normal vectors to the planes, which is easy because you just cherry pick off the components. And then the cross product of these two normal vectors happen to be the same as the direction vector for the line of intersection. Does anybody remember this?
Going back now.
Now, the hard part on the midterm problem was you actually had to find a point on that line of intersection. And there's different ways to do it, but one way is to force the z coordinates for both of the plane equations to be equal to 0 and then solve the two unknowns that you have left, which just have x's and y's, and then try to solve and find if there's an x and y coordinate, and then you have your x, y, and z coordinate, which would give you a point on that line, okay? There's some linear algebra way to do this problem, and I didn't give people full credit if they did it the linear algebra way, because this isn't a linear algebra class, although there are a lot of overlaps. I didn't want you to do it the linear algebra way, because if you only know how to do things the linear algebra way, and you're not willing to learn new ways of thinking in my class, because you're like, I'm just going to do it that way, I know what I'm doing, then you won't be able to extend that knowledge to this problem right here that we're just about to do. So this problem, they've got these two surfaces that intersect, and there's a curve right where they intersect. So if you can imagine this egg right here and this paraboloid, they're intersecting. And right where they intersect, there's a curve of intersection. And this curve of intersection kind of looks like it'd be an ellipse or something. It's right here. That's your curve of intersection. You know, or some people might say, well, it's down here, the way I see it. It's kind of hard. This is not a very good drawing. But you certainly could go to GeoGebra and these would sketch out pretty well. So at the point 013, which, you know, would be, I'm just going to make something up, 0, 1, 3, I don't know, maybe right here. There's your point P. If I drew a tangent line to that point, would you be able to give me the parametric equations? I'm going to try to draw a tangent line. There you go. Yikes! That's pretty gross. So basically, go get the, this is the tangent line to the curve of intersection. Go get the parametric equations for that tangent line. Oh, holy crap, how the heck are we going to do that? So the strategy is going to be very similar to this. So that's why I wanted to bring that up first. You're going to first get this written in the general form, fxyz equals 0. So that's not too hard because all I do is subtract 20 from both sides and I'm good. And then here's your big F. And you're going to go get his gradient. So you're going to go get big del F. So that's a normal vector to the surface, where when we were doing it back a few weeks ago, it was easy to find a normal vector to your plane because you just cherry pick it right off of the coefficients of your x, y, z. But here we're going to have to do a little bit more work because a normal vector to the surface, in this case, this guy right here is your ellipsoids equation right here. That's the egg. So you're going to get like a normal vector here. So we'll do, there's del F right there at that point. And then you're going to go get the other, the paraboloid, his equation. Here's the paraboloid guy right here. That's his equation. You're going to get everything on one side, and we'll subtract 4 from both sides, 0 on the other. We'll call this big G of x, y, z. And so here, you're going to go get the normal vector to that surface, big G. So we'll say, you know, I'll try to draw this a little better. I don't know. Let's say big G is pointing like this. And the claim is that when you evaluate big del F and big del G at the point, so big del F evaluated at the point P, cross product with big del G evaluated at the point P is going to give you a direction vector for your line. Okay, that's cool. That is like, wow, that is awesome. If you're not impressed, then you're not doing this class right. I don't know what to tell you. So let's go get del F and evaluate it at the point. Then we're going to go get big del G, the big gradient, and evaluate the point. Then we're going to take a cross product, and then I didn't say this problem was fast. I just said it was the last problem we were going to do. So big del F, this is the ellipsoid's normal vector to his surface. I get 2x, 4y, and 4z as the gradients components. And when I evaluate big del F at the point 0, 1, 3, what do I get? I'll just substitute here 2 times 0, 4 times 1, 4 times 3. And I get the component 0, 4, 12. Okay, fine. Save that for later. Now go get the other big old gradient for the paraboloid. So you're going to take his partials. And I get, I get 2x, 2y, and 1. And then when I evaluate that gradient at the point P, which has coordinates 0, 1, 3, I get, what, 2 times 0, 2 times 1, 1. So this component, these components are going to be 0, 2, 1. My computer is really slowing down right now. I don't know why. Let's plug in. And so let me append a page, and now it's time for cross product. And you know me, to get full credit in my class, and if you want full points on your MyMathLab, listen up. I want to see the 3 by 3 determinant. And I want to see I hat, J hat, K hat across the top row, please. And then you're going to have the gradient 0, 4, 12 components for gradient of f. Gradient of g is 0, 2, 1. Here you're going to have 4, 12, 2, 1 times I hat minus 0, 12, 0, 1 times j hat plus 0, 4, 0, 2 k hat. And then you get all these components, and I get, negative 20 I hat minus 0 j hat plus 0 k hat. And that's just in component form, that vector there. So it looks like it's pointing in the negative x direction. That's fine. And now you're ready. The parametric equations for the tangent line are, and we're easy peasy and we're done. This is the parametric equations for the tangent line to the curve of intersection. So the curve of intersection isn't a straight line like it is when two planes intersect. Here we're having a paraboloid and an ellipsoid intersect. So you're going to have x, y, z, and then the coordinates of the point are 0, 1, 3 respectively, and then you'll have negative 22, t, 1, and 3. And there's your parametric equations for the line, and we're done with this problem. So it's pretty cool, pretty exciting stuff, and that's another use for the 3D gradients right here in this problem. So I'm done. If you need to go, see you later. Goodbye. And thanks for